Is anyone else getting that NanoHub? It's like down. Same thing. Yeah. Yeah, might be. I know it said that there was going to be maintenance, but I can't remember what day it said maintenance was going to happen.
I don't know about I just know like some servers went down today.
Oh, on campus?
Not even on campus, just like in the world.
The World Wide Web?
Yeah.
Yeah.
Causing issues on sites.
Could be connected. Oh, Amazon Web Services. I don't know if NanoHub runs half internet down. Yeah. I don't know if NanoHub would be connected to Amazon Web Services. Maybe, but. All right, let's go back to nanohub.org. Give it one last try. Let me try. Morning. It does look like, so there's a banner up at the top of NanoHub saying that there's unexpected outages. There is an Amazon Web Services outage. Again, I don't know if it's connected. I don't think so, but it's possible. Okay, so let's take a look. Let's take a look at some of the concepts that we were working on anyway. I'm just loading up. run all, restart run all. So I wanted to talk about kind of what the state of a system is, because it's usually something that's a little weird. Like usually, if we're given a differential equation, there's just like we do a bunch of math to figure out how to solve that differential equation. But we don't have to do that, like especially if there is no solution. So what we can do is solve it with like numerical methods, like computational mechanics. And this one example is sort of like free fall, where acceleration is a function of velocity. You could even have like drag and spring force or friction. Like you can add whatever forces you want, it doesn't really matter, as long as you know like what is acceleration as a function of like position and velocity and time, like if there's any function of time. So general kind of setup that we're going to use for all these problems is defining all of the things that we're trying to solve for that we don't have an equation for. So state is our height and our velocity of this like falling, we could call it like a falling tennis ball. We have some kind of mg pointing down, we have drag pointing up. So what is the derivative of this state of that vector? Because now I'm describing position and velocity as like one thing called state. So what is the derivative there? Yeah, so the first one is velocity, so it's kind of like taking the second value and putting it in the first value. And then the next one is acceleration. And F equals ma, so we could cross this out and write sum of the forces over m. So if we know what forces are applied, then we know like change in the state as a function of the state. Because the change, so the velocity and the acceleration will be some function of that current state. It could be position, could be velocity. And that's like the general idea here. No question, I'm kind of slowing down for questions, but just doing fine, struggling with servers. All right, so what that looks like. MA equals negative, let's call it like C times V squared. I guess this one, so if we're gonna, drag is always going to oppose our motion. So if we're moving up, drag is pointing down. If we're moving down, then it's pointing up. So for a positive velocity, we have negative drag. For negative velocity, we have positive force of drag. So I'll get rid of the m's. So what's the first D state, the change in my state? I have an input of height and velocity. How do I calculate that first derivative of that current state? Which one? Just gravity?
Well, because the other thing is, like, is then derivatives, velocity, acceleration, so velocity and acceleration of it.
Oh, okay. So I think you're thinking of the second one. This one will definitely have like a negative g in there. Yep. But what about, what's the change in the height? Because that's what the derivative needs to tell us. How fast does our height change?
I'm confused about the 0 and 1, like, state 0 and state 1. What is that? Like, the number inside the brackets, what is that?
Oh, this is index 0. This is index 1. So I'm indexing to say like, and I didn't initialize anything, but I was just sort of like whiteboard coding, like what's the general idea of what I want to do. So when I say like D state 0, it's my very first input, so it's the change in my height. So how fast does, if you're falling, how fast is your height changing? Does it change with your acceleration? What's the derivative of your height? Like how fast you're moving? Derivative of position.
Is it just the velocity? But then if you say that the derivative of state 1 is just state 1? Or the derivative of state 0 is state 1, is that what it is?
Yeah, that's it. Yeah. Yeah, and it seems kind of weird that we're saying like the change of our first state is the value of our second state. But that it's just an exact definition that the change in position is velocity. So if velocity is one of our inputs, then it is the calculation of one of our outputs. And that's okay. And then this next one, we already said like that negative g is going to be in there, but we also have like a negative c over m, velocity squared, or we could do like velocity cubed over v. Just to get like the direction in there. And again, this is just sort of like a general, has like a little bit of Python, like I'm using Python indexing, but not doing like formal coding, just what is the concept of what we're trying to do. Ooh, excuse me. So if I'm falling from a height of 10 meters and my initial speed is 10 meters per second, how fast am I moving at this point in time? Because that's the output that we're going to calculate, and then we'll test it to see if we're right. At least if we can code it right. So how fast? Initial position is 10 meters high, 0 meters per second. So what's your initial speed? It's not a trick question. Yeah, 0. Yeah, I guess it's a trick question, but I don't know. What's our initial acceleration? Yeah. Gravity? Yeah, because we don't have any speed yet, so there is no drag yet. At least not yet. All right, so now let's take a look at the code to get us there. And this one just does acceleration. It's a good introduction, but I like the formal here. Oh, and this one is c equals 0, so that's fine. Because we're just testing out the zero speed. And sure enough, that's what we get. And the reason we go through the trouble of like taking position and velocity, turning them into a vector, is that we can integrate first order differential equations like with Euler method, and then there's a whole bunch of other really great first order integration methods. There are no second order integration methods, at least for a computer, because you need, and part of the problem is that you need to know, in order to know what forces are acting on it, in general you need to know what the position and what the velocity is. And if it's other things, like maybe you need, yeah, what else do you need? I'm trying to think of other second and third order differential equations. Anyway, yeah. But you need some of that information just to get what the current forces are. So we'll create first order differential equations. So your input is your initial condition, and then we can step forward in time from there. So like create a new vector of like the next height, the next velocity, the next. And closed. So now I have two outputs. One is this free fall, so taking our differential equations, plugging in initial conditions, and sure enough, I get the same thing. Like, it doesn't really matter what my initial height is. If I'm not moving, I'm gonna start moving. I'm gonna start accelerating, negative g. And then the next one is an Euler step of 1 dt time step. So what do you think that one is doing? Like, why is it 1.6 and negative 9.8 millimeters per second? What was our, do you remember the Euler steps from that, from project one? Homework one and project one? What was an Euler step? What is an Euler step? We had, in like one of our examples was like, the change in the population is equal to k times the current population. How did we do Euler steps to figure out like the next population? So I think we said, I forget. Let's say it was like population of 1900 was 5 billion. Zero, 1, 3, something like that. What's the Euler step to get to like the population in 1920? Yeah.
Isn't it just like initial plus derivative times time step?
Yeah. Yeah, so we're taking the initial, so the 5e6, plus that derivative, so k times p, and then multiply that by our delta t, so here 20 years. So we're using an initial condition, an exact, so it is an exact evaluation of our derivative, but we're saying that derivative is constant for 20 years, at least in this case. We can make it as small or as big as we want, but that was kind of what we did here. All right. I'm going to write S instead of state, and then H and B. Then my S dot, like ds dt. Oh, I'll write out ds dt. That's fine. Here it's going to be exactly the same formula. The only difference is now we're doing it with vectors instead of just a single value. So instead of just talking about population and change in population, we have height, change in height, velocity, change in velocity. But it's the exact same thing. And this can even get, like for find an element or CFD simulations, this might be 6,000 or 6 million different things inside your vector of like, what's this like point, what is this one point's position and velocity? What's the next point's position, velocity? Usually block it all into like all the positions and then all the velocities for like lots of things moving around. But it's still the same problem. So we have S of I plus 1 is S of I plus ds dt times that delta t. So we're taking that current state and adding an exact value of like what its change in state is, but approximating that it's constant for some length of time. So if I wanted to look at that, I could say, this is my derivative, multiply it by dt, and add numsol bracket 0, and then it's the same output, and that's what our Euler step is doing. And I'm stepping through this, like nobody specifically came and said like, please explain these methods to me, but it's usually a sticking point. This is a weird way of solving equations like this, but it's very, very powerful because now it's always the same solution process, no matter how complicated the problem gets. In a lot of the examples that we'll look at, it's kind of like 2 or 3 values in our state, so not a lot of degrees of freedom, but the same problems that we run into here are the exact same problems you run into in like dynamic finite elements and multi-body physics and all sorts of stuff. So that's why we keep it small. It's a lot easier to debug like 1 degree of freedom than 1,000 degrees of freedom. Yeah, yeah, that's right.
What do you do if you want, like, can you base another initial condition on what you find from the time step? Or is that not, like, if you do the time step to find whatever you want, and then can you use what you find to do another one, or is that not the way to do it?
Yeah, so what we're doing, that's what this step is doing. And I was going to ask you, what is this step doing? But that's exactly what we're doing here. Is like we're saying that if we start at index 0, so we know what's happening at time 0, we can move 1 step further, and now we have a value for index 1, so we can move on and say index 2 is the function of index 1, and kind of step one step at a time. Kind of, it sounds like exactly what you were describing of like, I have initial condition at 0, now I have initial condition at like, whatever, 1 second, and move forward from there.
But if you do more steps, do you get more error because it's continually based on something that's not exactly right?
Yeah, like we always introduce some error, but the smaller our time step, the closer it gets to an exact, there's no difference between our like handwritten solution and then like an actual computer result. And at some point we'll reach floating point error where we just get round off error. So even if we did have a better solution, there would be no difference.
So the number of steps doesn't matter, it's the size of the time step?
The size of the time step, yeah. The number of steps is related. Like if you're always looking at 0 to 3 seconds, like if you make the time step smaller, then there's more values. But yeah, somehow it's related. Mostly it's that delta t. Um, the fun way to talk about it is Taylor series expansions, which is everyone's favorite. No? No? No Taylor series? No. Somebody just got up and ran out of the room, left like a cartoonish hole in the wall, in the door. But like if you get like super into like, man, I love numerical methods, if only there was something more, if there were more proofs involved in all these coding examples, Taylor series expansions, that's the way to go. But if not, you can just be like, let me vibe code my way through this, and as long as DT gets smaller, you're in business. You'll get closer to the real answer. In this one, and in this case, like in this second reading that I'm kind of looking at, we're comparing like experimental measured data to the to a numerical solution. But really, one way to there is an error. So let's take a look at. We have up to 2 centimeters of error in our solution. Why do you? Yeah, actually, what do you think? How would you fix that error? There is error. At time 0, there's 0 error. So that one's good. Why is there 0 error at time 0?
You're given the initial condition.
Same initial conditions, right? Like you can't mess that up. You haven't done any Euler stepping yet, so we're good. All right, what else could we do? How else do we fix the error? Or do we need to fix it? Yeah. Yeah, we could just decrease this time step. And I know here, let's see if I can do this. Divide by 2, multiply by 2. It did something weird. Hit the ground. Oh, yeah, it does hit the ground. Over 2, over 2. Let's go int, int. And we want over 2. I thought I divided dt by 2. Oh yeah, we gotta go colon, 2. What? I'm doing something wrong. What did I do wrong? I tried to take dt divided by 2 to make it half the time step. Then I multiplied the number of steps by 2. So now dt is 1/2. So it should be n is double. Oh yeah, there's a do this. Why is it going on so long? It's matching. I think I made the time step smaller. I'm doing something weird because I divide time step by 2, so then there should be twice as many steps. Yes? No? Just me? I'm messing something up with my fancy code in here. T-num? Now it's 576. Now it's 576, so those should match. There we go. Error went up. That can't be right, because I decreased the time step. It should have gone down by a little bit. I'm messing something up. Something's weird. I don't know why I'm doing that wrong. All right, let's get it back to what it was. Deleted my bracket. There we go. All right, we're at least back to what it was, 2 centimeters. So what should have happened is that it should have stayed about 2 centimeters because we're already, like our delta t is really small already. Oh, you know what we could do? We could take 3 steps along the way. So for each, or 2 steps, we could just do 2. Let's do 2. So I'm just creating a midpoint solution and then another solution, just 2 half steps. And sure enough, it's basically 2 centimeters again. And even if I did it 4 times, it'll probably be about 2 centimeters because the time steps are already 1 millisecond, 1,000th of a second. What else could it be? We're looking at like the difference between an actual falling tennis ball and our solution of a falling tennis ball with drag. Do you think gravity is wrong?
I was gonna say that I think there's some rounding error of like drag coefficient or like gravity.
Okay. Yeah, how accurate is our knowledge of gravity?
I just mean like in what number we typed.
Oh, what number we typed?
9.8 or 9.81.
Okay.
I don't know.
Yeah, so we can go back up, figure out free fall. We use 9.81 for our like gravitational constant. So we could add more sig figs to that. Yeah. This one should be, oh, was it with or without? I thought it was with. Oh, no air resistance. Okay, there we go. Yeah, you're right. No air, okay, no air resistance, so we'll add it in. There we go. So now we're better. Instead of 2 centimeters off, we are 3 to 5 millimeters off. It's pretty good. Still not correct, but.
Why is so that graph, the y, is the difference between
Yeah, this one.
Because y is part of it negative and then part of it positive.
This is num sol minus so it's our numerical solution minus the experimental height. So we measured, at least in this case, there are 576 data points of where the tennis ball was, and then we have our predicted solution of where it is. So it got better as we added drag. Yeah, and the time step, for the most part, we're kind of converged, probably, for Euler method. We could probably get it'll change a little bit less. Is this the right drag coefficient? 0.47? I don't know. Depends on the tennis ball, right? I think this one's assuming that it's a sphere. We could probably look up. Yeah, you don't want robots figuring out what the drag on a tennis ball is. Oh my God. This is way too much information. Let's see, what did it come up with? This one says 0.5, depending on the Reynolds number. Let's call 5-1. And it drops a little bit, right? So what we could do is actually use this to figure out, like, try to minimize that error based on what that drag coefficient is. One way to kind of use this method, but another way is just like, yeah, I did it, I tried. Okay, hopefully that helps kind of with this like new method of integrating differential equations, but pure coding wise. So we're just splitting it up, turning it into 2 first order differential equations, depending on what order it is, but 2 first order, and then integrate that first order over time. Cool, thanks a lot. Thanks for braving the rain to get here. I'll see you Wednesday.